Hello everyone, welcome to my week 10 project that is on hyperelasticity, strain energy. A quick overview of what I'll be discussing in this presentation. So I'll be briefly going through the parameterization of my 3D body. Then I'll be choosing a displacement field on that body, and I'll compute the corresponding displacement gradient tensor by taking partial differentiation and the linearized strain tensor. Then I'll define material properties, that is modulus of elasticity and the Poisson's ratio. Using this formula, I'll compute the stress tensor field and then the stress energy density. And finally, I'll verify stress energy for one body using hand calculations, and we'll see that if we get the same solution as that we obtained from MATLAB. So the body I've chosen is an I section, and here is the parameterization. The depth of the section is 6 units, the length is 12 units, width of flange is 5 units, and the thickness of flanges and webs are 0.5 each. So the displacement field I've chosen is this, that is in x, y and z direction. It's 2z, 2z and x plus y. I've kept it linear so that my calculations don't complicate enough. This is the corresponding displacement gradient which we get obtained from taking partial differentiation. And if we multiply, if we add this thing with its transpose and take half of that, we get the linearized strain tensor, which is this, and the Cauchy stress tensor is computed by using this formula. In this case, our trace for the linearized strain tensor comes out to be 0, so our Cauchy stress tensor basically becomes just this term. So I have written it accordingly. Now coding it into the MATLAB, the displacement field is coded in such a way, the corresponding strain tensor and the material properties. We get an output window, output of the strain energy stored in each of the body as 207 and the thing, and this is the corresponding deformed shape. Now we can do the same thing by hand calculations too. For that, I've chosen all my units in, like, the length is in centimeter, mass is in kg, and time is in seconds, and I'm consistent with these units only. The Young's modulus I've chosen is 200 into 10 raised by 9 Newton per meter square. Poisson's ratio is 0.3. So the strain energy density is given by half of dot product of strain tensor times Cauchy stress tensor. So using this formula, I have substituted accordingly, and I obtain the strain energy density as half times modulus of elasticity divided by 1 plus nu times taking the dot product, we get this term, and this sums up to be 9. And I've performed this integral substituting according the proper limits, and using Wolfram integral tool, I get a value as 2.076 into 10 raised by 11, and the same thing I have obtained from MATLAB too. Now I'll quickly show my code. So here is the deformed shape and the command window. So indeed I get the same value as stated in the presentation. Thank you.